Hi everyone. Today let's talk about section 6.2, area between curves. Big idea. The integral can be used to compute the area between two curves, besides area under a curve. In Calculus 1, the last chapter, we talk about how to find area under a curve. That is the definite integral. Right? Today we're gonna expand a little bit. We will talk about area between two curves. Big skills. You should be able to look at the graph of two functions and be able to calculate the area between them. Okay? So here we have the picture. We have two functions f and g. F is greater or equal to g of x. Okay? And this is the region. So this is the area between those two curves, right? And from x equals to a to x equals to b. And what do is, well, similar to what we have done in chapter 5, we're gonna divide this region into a lot of rectangles, and each rectangles we're gonna approximate it. So let's look at each rectangles. You can see the width is change of x, and the height is actually f of so we pick any points in this interval. So let's pick this point xi star, and then f of xi star minus g of xi star is gonna be the height of this this rectangle. Okay, and then we have so many rectangle. Then the area of the region, okay, is the Riemann sum. Okay, it's the sum of the area of those approximating rectangles. So we have the limit n goes to infinity, and then the sum of the area of the rectangle, which is the height, times the width. Okay. So that's why here we have the formula. Suppose f and g are continuous function with f is greater or equal to g on the interval a to b. Then the area of the region bounded by the graph f and g on the interval ab is given by area is the definite integral from a to b, f of x minus g of x dx. Okay, so it exactly corresponds to our Riemann sum. Okay, that's the area of the rectangle. Okay, so let's look at example 1. So we want to find the area of the region bounded by the graph f equals 1 over 1 plus x squared, and g equals x minus 1/2, and the y-axis. So first we need to graph them. Okay, please remember all the graphs of the common functions, and also, this is not the common functions we learned, but we know this is rational functions. If you don't remember the graph of the functions, it's okay. It's okay. We can plot some points. Okay, we can plot some points and then connect them smoothly. So if you forgot the graph, it's okay. Don't be scared. Just plot some points and connect them smoothly. Okay, so here we have, oops, let me draw better. So we have x-axis and y-axis. So let's first graph the function f. So we plug in x is 0, then we get 1. So when x is 0, we get 1. So we pass through this point. And when x equals 1, we get 1 over 2, right? So this is 1. We'll get 1 over 2, which is right here. When x is 2, we actually get 1 over 5, right? So let's say it's somewhere here. So then we can connect them. Oops. Okay, so we can connect them smoothly. And you can see when x is getting bigger, our denominator is getting bigger, so the number is getting smaller, it goes to 0. Okay, and also, do you realize the x squared make the function to be an even function? So when you plug in minus 1 squared is 1, so we still get 1 over 2. Right? So that's why this is an even function. We also pass through this point. So this is f. How about g? Well, g is a linear function, then we know it's a line. So how many points can fix a line? 2 points. So we actually just need 2 points. The first point that we can pick x as 0, then we get minus 1/2. And the second point we can pick x to be 1. 1 minus 1/2 is 1/2. Oh, you see, we find the intersection points. Okay, so we can plus some points, and then we can also find the intersection points. So to find the intersection point, you don't need to solve the system of equation here. So I can promise you, usually the intersection points of the graph are a simple number, is either integer or a very simple fraction. So you can see from the graph, okay? Alright, so this is G, and we're looking for the area bounded by F, G, and the y-axis. See, this is the y-axis. So, oops. So this is the area we're looking for. Okay, let's continue. So area equals our x. Where's our x? So you can see the x value. X is from 0 to 1, right? So x goes from 0 to 1. The upper function, which one is the upper function? The f is the upper function. So 1 over 1 plus x squared minus g. G is x minus 1/2. Oh, be careful. Don't forget your baby parentheses. Okay, if you forget the parentheses, then it will be wrong. So be careful with that. And next, let's distribute. So it's minus x and then plus 1/2 dx. Okay, let's integrate. Well, what's the integral of 1 over 1 plus x squared? Well, that is arctangent, right? So this is arctangent of x. Integral of x squared over 2, integral of 1/2 is just 1/2 x. And then after we're done, we evaluate from 0 to 1. It means we plug in 1 first. And then we plug in 0. Okay. Alright, so what is arctangent of 1? So when I draw the arctangent, when I want to find the arctangent values, I always draw the tangent. Because I know arctangent and tangent, they are inverse functions, right? So the x values of the arctangent corresponds to the y value of the tangent. Okay, so x value of the arctangent corresponds to the y value of the tangent. So this case, x values is 1, so that corresponds to the y value of the tangent is 1. Okay, so what is this guy? This guy is pi over 2, right? And so what is this guy? Pi over 4. So this is pi over 4, and minus 1/2 plus 1/2, they cancel. And then arctangent of 0, this means, oh, if my y value is 0, what's the corresponding x values? Also 0, right? So that's why our answer for this problem is pi over 4. So far, so good, everybody? So let's continue. Example 2. Find the area of the region bounded above by the x-axis, bounded below by y equals x cubed, and bounded on the side by x equals minus 1. So I hope you can pause the video here and try to work on this problem first. Are you done? Let's check our work. So we have the x-axis. Oops, let me draw it better. Okay. This is x, this is y. And the curve we're looking at x cubed. Do you know what this x cubed looks like? It passed through 0, 0. It passed through 1, 1 and minus 1, 1, right? And the shape looks like, oops. Okay. Alright. Okay, so this is x cubed, right? Okay, we're looking for the region bounded below by x cubed. So it means x cubed is below that region, bounded above by the x-axis. So x-axis is above that region, and bounded on the side by x equals minus 1. So we are looking at this region. Okay, bounded above means x-axis is above that region. Bounded below by x cubed, it means x cubed is below that region. Okay, and this is the region we're looking for. Okay, so let's see. Area equals integral. So x goes from minus 1 to 0. What is the upper function? Well, the x-axis, what's the x-axis? That corresponds to y equals 0, right? It's a line, it's y equals 0, minus the lower function, which is x cubed. Alright, let's see. Integral of x cubed, we add 1 to the exponents, divided by the new exponents, evaluate from minus 1 to 0. It means we plug in 0 first, that's 0, minus, we plug in minus 1. So we minus, but there's not a negative, okay? And then minus 1 to the 4th is actually 1. Okay? So minus cancel, and this guy is 1. So our answer is 1 over 4. So far, so good, everybody? So that is example 2. Let's continue. Example 3. We want to find the area of the region bounded by y equals x, y equals cosine x, y equals 0, and pi over 6. So let's draw the region. So yeah, so all of the common function, I hope you remember how to graph it. So cosine and sine, they're oscillating between minus 1 and 1, but cosine start from what? 1, right? So it oscillating, and this guy is pi over 2, right? And you know, pi over 2 is approximately 3 so pi is 3.14, right? Divided by 2 is 1.57. So 1.57 is around right here. So y equals x is this guy. Okay, at pi over 2, the y value is also pi over 2. Okay, this is y equals x. And we want to bound it between 0 and pi over 6. Okay, what is pi over 6? Well, you take you divide it into 3 pieces, then this guy is pi over 6, right? So this is the region. A bounded by y equals x, y equals cosine, and x is 0, x is pi over 6. So this is the region. So sometimes I recommend you to draw the picture big enough. So sometimes I see students, oh, draw this, and then this is so tiny, and then student cannot really see whether the bound is bigger or smaller. So it's better to draw a bigger picture, then you can see the graph, okay, more clearly. Okay, so next, our area is the integral. So my x goes from 0 to pi over 6. And then the upper function is cosine x. The lower function is x. Okay, so what is the integral of cosine? Well, you think about, okay, we know it must be sine or minus sine, but we think about the derivative of sine is positive cosine. So integral of cosine is positive sine. Integral of x, x squared over 2. Evaluate from 0 to pi over 6. Well, this means we plug in pi over 6. Subtract. Okay, so pi over 6 squared over 2, right? And let's see. So we have sine pi over 6. Well, do you remember what is the sine pi over 6? I hope for the for the common angle value you can remember it. Okay? So what are the common angle values? Oh, they are like 0. Sorry. I mean, x is 0, pi over 6, pi over 4, pi over 3, pi over 2. And the sine x, well, the sine x is 0, 1/2, root 2 over 2, root 3 over 2, and 1. How to remember this? Well, you remember the root of square root of n over 2. So then this guy is like probably n equals 0. This guy is like probably n equals 1, n equals 2, n equals 3, n equals 4. And then you get all those numbers. Okay, so remember this rule. And then how about cosine? Well, cosine are the same number, but you just reverse the order. Okay, and furthermore, you can continue with tangent, cotangent, secant, and cosecant. So let me see. Do we have enough space here? Okay. Okay. So well, we can continue. So tangent. Remember, tangent is sine over cosine. So 0 over 1, 0. 1/2 over root 3 is 1 over root 3. Same thing over same thing. So 1. Root 3 and with the half cancel, right? 1 over 0 is undefined. So actually we have a vertical asymptote at pi over 2, right? And cotangent is the same thing but reverse order. So we have undefined square root of 3, 1 over square root of 3, and 0. How about secant? Well, secant is 1 over cosine. Well, then 1 over 1 is 1. And this guy, 1 over that, it means you flip it over. So 2 over root 3, 1 over that is actually root 2. 1 over that is 2. 1 over 0 undefined. So we also have vertical asymptote. Okay? At pi over 2 for secant. How about cosecant? Same thing as the secant, but reverse order. Okay, and those are all the common values for the 6 trig functions of the common angles. Okay, so sine pi over 6, which is 1/2, minus, this guy, pi squared over, this is 36. But when you divide it by 2, it means, remember, a over b over c over d equals a over b times d over c. So the 2 is like the c is in the denominator. So our answer is 1/2 minus pi squared over 72. See, we can calculate without a calculator. I strongly recommend you when you do your homework or exam problems, try not to use your calculator. If you want, you can use your calculator to check your work, but not during your calculation. Okay, so it's good to build up the sense with the numbers. Okay, example 4. Let me change a different color because we have some overlap there. Okay, so we want to find the area bounded by the parabola and the line. Okay, so how do we draw the parabola? Alright, so we know because the leading coefficient is positive, we know it's going to be opened up. But let's look at this guy. Can you see we can factor out x and then we get x minus 2? So then I know the x-intercept is 0 and 2. Okay, so and I know the parabola opens up. So let me see. So 0 is here, 2 is here. So our parabola Oops. Okay, our parabola look like this. So far, so good, everybody. And our line y equals x plus 4. We know 2 point fix the line, so we can plug in 0. Then we get 4, right? Let's see. Okay, let me draw a different scale, okay? Because the graph is okay. Let's say 4 is right here. Then when x is 1, we get 5. Okay, so just connect them together. Okay, so we know there are 2 intersections. Okay, so how do we find those 2 points? Okay, so remember I promised you that the intersections is gonna be easy numbers. So we, instead of solving the system of equations, you can actually just plug in some number and see to find whether some number pass through both of them, and then those are the intersection points. Okay. Because later on I might give you the functions. Maybe it's not quadratic functions, maybe it's higher order functions or square root something functions, so it's hard to solve the system sometimes. Okay, so but I promise you the intersection points are easy to find. Okay, here let's try -1. See, from the graph, why don't we try -1 and see whether it works? So when we plug in -1, -1 squared is 1. 1 minus 2 times -1 become 1 plus 2, which is 3. Oh, okay. So the y value is 3. How about this guy? When I plug in -1, oh, -1 plus 4 is also 3. See? They actually meet at -1 and 3. So this is the intersection point. So far, so good, everybody. Okay, and then next, oh sorry, this 0 looks like a 10 there. So let me put a 0 here. Okay, so here, I know this number is bigger than 2, so let me try 3. 3 squared, 9 minus 2 times 3, 6 is 3. 3 plus 4, which is 7. That's not the intersection point. So let's go to 4. Let's see whether 4 works. 4 squared, 16 minus 2 times 4, 8 is 8. Oh, 4 plus 4 is 8. See? They match. So they meet at 4 and 8. So far, so good. See, now we have found the 2 intersection points. So we want to find the area bounded between the curves. So area is my x goes from, you see the region? If you look at the x values, the smallest x value is -4. The largest is, the smallest x values is -1. The largest is 4. And the upper function is the line. The lower function is the parabola. Alright, let's distribute it. -x squared plus 2x. So we can combine the like terms together. We will have 3x plus 4 minus x squared. Okay. Let's integrate 3x, become 3x squared over 2. 4 become 4x. And this is x cubed over 3, right? This is the integral. We add 1 to the exponent and divide it by the new exponent. Evaluate from -1 to 4. That means we plug in 4 first. So 4 squared, 16. 4 times 4 is 16. Ooh, 4 cubed, 64 over 3, minus, parentheses, don't forget your baby. When we plug in -1 squared is 1. And -1, so -4. -1 cubed is still -1, so minus become positive. Okay, now let's see. This cancel, we have 8. 3 times 8 is 24. 24 plus 16 is 40. So 40 minus 64 over 3 minus 3/2 plus 4 minus 1/3. Okay, now let's see. That is like 44 minus So we combine this guy and this guy together. I get 44. And then I combine the 64 over 3 and then 1 over 3 together. So that's 65 over 3. And then I still have the minus 3 over 2. Okay. The common denominator. So let me combine the first two guys together first. So that's 3 times 4, 12. Oh, 132, right? Minus 65 equal, and then don't forget the minus 3/2. Okay, so 132 minus 65 is 67. Right? So 67 over 3 minus 3 over 2. Oh, the common denominator is 6. 67 times 2 is 134. 3 times 3, 9. So we have 125 over 6. Okay, so feel free to plug this number in your calculator to check our work. But in the process of getting this number, I strongly recommend you to practice of calculating on your own. Okay? Alright. So far so good, everybody. So that's the area between the two curves. And in that example, we need to find the intersection points. So just try to plot the points near them, and then you can find the intersection points. So example 5, let's continue. Find the area of the region bounded by y equals square root of x plus 3 and y equals x plus 3 over 2. So here, we want to graph square roots. What square roots looks like? If you can remember, square roots looks like that, right? So we're going to plot some points, and then we connect them smoothly. Okay, so what points we want to plot? So, what square roots? Okay, what is the smallest x we can get? Remember the things inside the square root cannot be negative. So the smallest x we can get is minus 3. Then you will have 0 in the square root. So when x is minus 3, the y is 0. So this is the smallest point. This is like the vertex of the square root function. And well, you see when you plug in 0 for x, you get square root of 3, and that's not integer. Let's try to plug in the x value such that we get integer. What x value can give us an integer? Probably minus 2, right? Then 3 minus 2 is 1. Square root of 1 is 1. So this is 1. And then next integer, square root of 4 is the integer. That means x is 1. So x is 1, and then we have square root of 4, which is 2. And then what's the next integer? Well, square root of 4 and square root of 5 is not an integer. Square root of 6, square root of 7, square root of 8, square root of 9. Square root of 9 is an integer. That is when x equals 6. So 1, 2, 3, 4, 5, 6. And square root of 9 is 3. Okay. So see, we connect those points smoothly. This is square root of x plus 3. Okay, so try to plot the integer point. And then next, y equals x plus 3 over 2. This is a line. 2 points can fix a line. You can see when we plug in x is minus 3, the numerator is 0. We also get 0. So see, we get 1 intersection point. Oops, did I choose the... Okay, yeah. So you see, it also passed through -3 and 0. What number can make it to be an integer point? I would say probably x is 1. When x is 1, you get what? You get 1 plus 3 is 4. 4 over 2, 2. So 1, 2. Oh, that is exactly another intersection point. You see? When we find those intersection points, we actually when we graph it, we find the intersection points automatically, right? Okay, so this is our region. We want to find the area of this region. So A is integral. My x goes from -3 to 1. And the upper function is the square root function. And the lower function is the linear function. Okay, so we can do x plus 3 over 2 dx. Okay, so how to integrate them? Well, let's split. Okay, we have this guy. Well, this guy is the same as so integral of, we can put out the 1/2 and then it's just x plus 3 dx. So the second integral, we know how to integrate. Just the first one, we need some methods. Do you remember that methods? U substitution, right? It's a composite function. So we let u be x plus 3 and then du is dx. Well, so the first integral is just u of -3. So u of -3 and u of 1. And then square root of u du, right? So let's just call the first integral be I. Okay, so the I equals this guy. And then this is like u to the 1/2, right? So this is u to, okay, when we plug in x is -3 and then u is 0. When we plug in this, we get 4, right? This is the u to the 1/2 du. The integral of that is u to the 3/2 over 3/2, but the half you flip it on top. Evaluate from 0 to 4. We plug in 4 first. 4 square root 4 to 2 cubed is 8 minus 0. Oh, that's 16 over 3. Okay, and then so our answer equals A equals 16 over 3. And then the second integral, we have x squared over 2 plus 3x. Evaluate from -3 to 1. Oops, my minus looks like a dot. So let me write it better. Okay, so this means we plug in 1 first. Subtract when we plug in -3, but don't forget the parentheses. -3 squared is 9. -3 times 3, -9. Okay, so let's see. This is 1/2 plus 3 minus 9/2 plus 9. 1/2 minus 9/2 is minus 8/2, which is -4. 3 minus 4 minus 1 plus 9 is -1 plus 9, 8. 1/2 times 8 is 4. So this is 16 over 3 minus 4. Well, that's common denominator, 16. 4 times 3 is 12. So this is 4 over 3. So far, so good. You can try to plug this in our calculator and check our work. Okay. So far, so good. Okay, and then next, integrates with respect to y. So what we have done, we cut the rectangle vertically, and the width is change of x. However, for some of the functions, for example, if f and g are continuous function with, so x is a function of y, and f is greater or equal to g of y on the interval ab, then the area of the region bounded by the graph. Okay, so the picture is like this. So you have this is f and this is g, and you want to, let's say, evaluate from this is a to b. So remember, the bigger function now is on the right hand side. The smaller function is on the left hand side. If you want to evaluate this region, what do? You you cut those rectangle horizontally, so you get a lot of horizontal rectangles. Now, what is the width? The width is change of y, okay? And then the height is f of x minus g of x is the height. Okay, so that's why this is our new formula. It's very similar, you just replace x by y and they work the same way. Okay, so let's continue. We want to find the area of the region bounded by those two functions. Okay, so let's grab them. Okay, so the first one is easy. Y equals x minus 1. We know it's a line. So let's plug in some number. 2 points can fix the line, right? So we plug in x is 0. We get minus 1. So that's 1 point. We plug in 1. We get y is 0. Oh, so this is the line. Oops. Okay, so this is the line y equals x minus 1. Okay, second one. This is a, you see the y has degree 2, x has degree 1, so this is a parabola, but so this parabola is actually opened to the right. Because x is the function of y, okay? And the leading coefficient is positive, so it opens to the right. If the leading coefficient is negative, then it opens to the left. So we can solve for x. X is y squared minus 6 over 2. So this is like 1/2 y squared minus 3. So let's see. Well, can you see when we plug in y equals 0, we get x is 3. So y is 0, x is negative 3. So negative 3 is here. So it passed through this point. And, well, we want to work with integer, right? So we want to work with integer. So if we pick y equals 1, it won't give us integer. So let's plug in y equals 2. So when we plug in y equals 2, what do we get? 2 squared is 4 over 2. So 2 minus 3 is minus 1. So when y equals 2, we get x is minus 1. Okay, so it's this point. And also when y equals negative 2, we also get minus 1. So negative 2, this is minus 1. Oh, it looks like this is the intersection point. Let's see whether this point is actually on the line. So we plug in x is minus 1, then y is minus 1, minus 1. Oh, minus 2. See, this is actually the intersection point. So good, we already find one intersection point. So we can connect them smoothly. And this guy, okay, we know there must be another intersection point. Let's try to find it. Okay, remember we want to find integer. Okay, so we will plug in y equals 3, but it won't give us integer, so let's plug in y equals 4. So 4 squared, 16, 16 divided by 2, 8. 8 minus 3, 5. So it passed through, y is 4 and x is 5. So let's see whether this point is on the line. So we plug in x is 5, 5 minus 1, 4. Oh, that is actually the intersection point. So I know this x value is 5, the y value is 4. And we are looking for the region bounded by them. So far, so good, everybody. Alright. Oops, sorry. I just realized I had a mistake here. So, I mean f of y minus g of y. Okay? Because now, we're doing the horizontal distance. You know, any graph, the horizontal distance is x, the vertical distance is y. So the height is actually the difference of the horizontal distance. So it's the difference of x. Okay? So, and x is a function of, y. Okay, so in this case, area is, so this is the integral about y. So where do my y goes? is the smallest number is -2. The biggest number is 4. So be careful. Many students put the x values here. No, we're talking about the y values. This is an integral about y. And then we don't say upper and lower function. The bigger function is the function on the right. We can see the line is on the right. So it's x plus 1 minus the parabola. But the parabola you want to, oh, sorry, I almost made the mistake. Remember, what do we want to plug in? We want to plug in the x is a function of y. So you can plug in x minus 1. We want to have a y integral. So you need to solve for x. X is actually y plus 1. So y plus 1 minus the other one parabola is 1/2 y squared minus 3 dy. So far so good, everybody? So be careful. This is the integral about y. So we want to express. So express x in terms of y. So be careful with that. And then we can get rid of the parentheses. So this is y plus 1 minus 1/2 y squared minus become plus 3 dy. Oops. We can combine the like terms. So y plus 4 minus 1/2 y squared dy. Okay, let's continue. So that equals the integral of y squared over 2, integral of 4 y. And this is y cubed, so divided by 3, so 1 over 6. We evaluate from -2 to 4. So which means we plug in 4 first. 4 squared, 16. 16 over 2, 8. 4 times 4, 16. 4 cube. 4 cube is 64. 64 over 6. There's a common factor 2. So that's like 32 over 3. Minus, we plug in -2. -2 squared, 4 over 2, 2. -2 times 4 is -8. -2 cube is -8. Negative cancel. So 8 over 6 is the same as 4 over 3. Okay, so 8. Okay, let's see. 8 plus 16, 24 minus 32 over 3 minus, okay, 2 minus 8, -6, minus become positive 6, and minus 4 over 3. So 24 plus 6 is 30, and 32 plus 4, see, it's minus 32 plus 4. So 32 plus 4 is 36. 36. Well, 36, we can divide it by 3. That's 12. So 30 minus 12 is 18. So you can try to plug this number in your calculator to check whether you have 18. So far, so good, everybody? So the good thing about videos is you can pause at any time and think more, and also you can watch the video again and again. If you have questions, feel free to print screen and ask me. Okay? Alright, let's continue. Find the area of the region bounded by the graph of y equals x cubed and y equals x plus 6 and the x-axis. Okay, so let's see. X cubed, we know x cubed look like this, right? Okay, how about x plus 6? Oh, okay. We know when we plug in x is 0, we get 6. Okay, 0 gets 6. And when we plug in, okay, we plug in x is 1, we get 7. So, and we also want to know where do they intersect. You know, x cubed, when we plug in x is 1, we get 1. When we plug in x is 2, we get 2 cubed is 8. Oh, do you see 2 plus 6 is also 8? So actually, one of the intersection point is here. Oh, okay. So we know the line passed through this point and that point, and we are looking for the area of the region bounded by the graph y equals x cubed, y equals x plus 6, and the x-axis. So this is the region we are looking for. So far, so good, everybody? Okay, so if we want to calculate the area, we gotta be careful because do you see this region, this guy? By the way, what is this guy? When y equals 0, the x is minus 6, right? Well, you see this orange is a triangle. Okay, and the upper function is the line, the lower function is the x-axis. So, and then the other pieces, the blue region, the upper function is the line, and the lower function is the cubic function. Right? So that's why when you calculate the area, you need to split into 2 regions. So area is actually, so integral from minus 6 to 0, and the upper function is the line. The lower function is the x-axis. This is the orange area. But we know because this is a triangle. Right? This is a triangle. Well, triangle is 1/2 base times height. Well, the base is 6, height is also 6. So, but okay, if you have time, feel free to calculate this integral to see whether you get the same answer. Okay? Yeah, it's good to practice that. And then the blue area is x from 0 to 2, and the bigger function is the line. The lower function is the cubic function. Okay, so integral is x squared over 2, 6x, x to the 4 over 4, 0 to 2. Okay, let's continue. And what do we get? So 2 and 6 cancel, we get 3. 3 times 6, 18. And we plug in 2 first. 2 squared 4. 4 divided by 2, 2. 2 times 6, 12. 2 to the 4th, 16. 16 over 4, 4. Oh, when we plug in 0. 0 is really a lovely numbers. Save a lot of work. 2 plus 12, 14. 14 minus 4, 10. So this is 18 plus 10. And we get 28. So far, so good, everybody? Okay, let's continue. Example 8. We want to find the area of the region bounded by the graph y equals x to the 2/3 and y equals x minus 4 and the x-axis. Okay, so let's draw it. Well, we know x minus 4. It passed through when x is 0, we get -4. And when x is 4, we get 0. Okay, so this is the line. We draw the line first. The line is easier to draw. Okay, next. Well, this is x to the 2/3. We don't have a graph for this functions, but we can plot some points and connect them smoothly. We can plug in x is 0, then y is 0. We can plug in x is 1. We get 1, right? Okay, next. Cube roots. We want to have integer points, right? Cube roots, well, cube roots of 8, we know, right? So I suggest that we should consider to plug in x as 8 because we want to work with integer. Then cube roots of 8. So it's 8 to 2/3, right? Cube root of 8 is 2. 2 squared is 4. Oh, so my y value is 4. What happened? That is actually the intersection point. See, when we are plotting a function and you find integer point to plug in, and then you can see the intersection points automatically. Okay, so try to plug in integer points. All right, and let's continue. Okay. Yeah, so this is the problem. I asked you to like put points to find the intersection points. Otherwise, when you want to solve the system, oh, you get x to the 2/3 equals x minus 4. Well, this is not a polynomial function. we're only able to solve linear function and quadratic function because we have quadratic formula, and then these kind of function we're not able to solve. So it's okay. You can still plot integer points to find the intersection points. Okay, so now we want to find the area of the region bounded by them and the x-axis, so which is this region. Oh, okay. So, what happened? Well, do you see this on the left? The upper function is the curve. The lower function is the x-axis. Okay, but on the right hand side here, the upper function is the curve, the lower function is the line. So, and the bad thing is this guy is not an integer point, so it's not easy to calculate. So for this problem, there are two ways to solve. You either split into two intervals like we did from the previous example, and then you calculate the area from 0 to 4, and you calculate the integral from 4 to 8. That is one way. And the other way is you can see if I cut it horizontally, then I don't need to split into two integral. Right? If we can cut it horizontally, then the upper curve is always the line, the lower curve is always the curve. Okay, so far so good, everybody. So let's cut it horizontally. Then we have dy. So solve for x in terms of y. So here x equals y is 2/3, now it's 3/2. Okay. This guy x equals y plus 4. Then area is, my y goes from 0 to 4. Upper curve is the line, y plus 4. Lower curve, the curved y to the 3/2 dy. And this is y squared over 2 plus 4y. And we add 1, which is 5/2 over 5/2, but 2 we can flip on top. Evaluate from 0 to 4. We plug in 4 squared, 16, 16 over 2, 8. 4 times 4, 16. Oh, square root of 4 is 2. 2 to the 5th, 32. And when we plug in 0, it's all 0. Oh, 0 is such a beautiful number. 8 plus 16, 24. And this is 64 over 5. Common denominator 5. 5 times 4, 2. 5 times 2, 10. So 120 minus 64. Okay, what is 120 minus 64? That is 56. So far, so good, everybody. So the answer is 56 over 5. Okay. So far, so good, everybody. We have some time left. So maybe we can, I also want to, maybe we can try to cut it vertically and see whether we get the same answer. This is a good exercise because you can choose to cut it vertically or horizontally. But when you cut it vertically, you need to separate into two integral. Okay, so area is integral. X goes from 0 to 4. The upper function is the this curve, the lower function is the x-axis, which is y equals 0. And the second integral, x goes from 4 to 8. The upper function is the curve. The lower function is the line. And don't forget your parentheses. Well, you see, those numbers are already harder than our previous integral. So let's try it. Okay, we add 1 to the exponent. So 5, 3, 5, 3 on top, 0 to 4. Here, x 5, 3, 5, 3 from 4 to 8. Minus, okay, this is a minus x plus 4. So minus x squared over 2 and we also have 4x. Okay, so we also everything evaluates from 4 to 8. Okay, so look at this guy. You evaluate from 4 to 8 and plus you evaluate from you evaluate from 0 to 4 and then evaluate from 4 to 8. It's the same as you evaluate from 0 to 8. Okay? Okay, so this can save us a little more time here. Okay, and this is 4 to 8. Okay, so let's see. We plug in 8. Cube root of 8 to 2 to the 5th, 32. We plug in 8 first. So we plug in 8. 8 squared, 64 over 2, 32. 8 times 4, 32. Minus negative. Okay, so when we plug in 4, it's negative 4 squared, 16 over 2, 8. 4 times 4, 16. Okay, so we get 3, so 96 over 5. These cancel. Here, this is the 6, right? Sorry, 8 minus 8 plus 16 is 8. So minus 8. The common denominator, 96 minus 40 is 56 over 5. You see? It's the same answer. So no matter we cut it vertically or horizontally, we get the same answer. And it makes sense. So for all of the integrals, you can think about to cut it vertically or horizontally, which way is easier and which way. So in this problem, obvious, cut it horizontally. Integral of the dy is easier, right? So how about the previous example? So the previous example, you can also choose to cut it horizontally. Then you have an integral about y. And then you also will have one piece. So far, so good, everybody. Do you want to work with me? What happens if you want to calculate? If you want to cut it horizontally? Yeah, it's good to have more practice, right? So, okay, let's try to do it. If we cut it horizontally, then you want to solve for x. So first, the curve become cube roots of y, and then the line become y minus 6. Well, then now my y goes from 0 to 8 upper. So bigger function is the curve. So y to the 1 cube minus smaller function is the line, dy, right? And then minus y plus 6. All right. And so you can see we can add 1. So 4/3 over 3 on top. Y squared over 2. 6y. Evaluate from 0 to 8. So 3 over 4. Okay, 8. We plug in 8. So 8 to the 4/3. 8 squared, 64 over 2, 32. 8 times 6, 48. When we plug in 0, all 0. Such a beautiful number. So cube root of 8 is 2. 2 to the 4th is 16. 16 and 4 cancel, we get 4 on top. 3 times 4 is 12. So 12, 48 minus 32 is 16. So 12 plus 16, 28. You see, we have the same answer and it makes sense. So for more practice, if from now on, if you're able to do it both ways, so calculate vertically and calculate horizontally, so I hope you can try both ways. Okay, and then you can see whether you get the same answer. If you don't get the same answer, something is wrong, and then try to find your mistake. Okay, we learn from our mistake. I strongly recommend you to have a mistake book to collect all of your mistakes, and then before the exams, you can review your mistake book and sort of remind you to not make the same mistake again in the exam. Okay, this is how we learn. And that's it for this session. So this session is 6.2. We learned about the area between curves. Have a good day. Bye.